Good morning. I can't tell you how pleased we are to have Jack Newman join us. He is the type of individual that DARPA seeks to attract. Somebody with vision, somebody who's entrepreneurial, and somebody who realizes that solving many of these challenges goes way beyond a single academic lab, a single company, and a single field. This is what DARPA was built for. I need a clicker. Yeah, thank you. This is what most of us think about when we think about advanced technology. We think about autonomous robotics, virtual reality headsets, hypersonic vehicles, the Internet of Things. This is the most advanced technology, though, that I know of. Biology can do things that no other technology can come close to doing. It can replicate itself. It can adapt. It can evolve. It can scale from 1 to millions to billions effortlessly in a day. And it's programmable through the genetic code. Biology is technology. But the problem is we have no idea how to harness this capability today. Our tools are so febrile. And as we enter the 21st century, it's becoming apparent that many of the technologies that we relied upon in the 20th century that gave us all of these technological revolutions have passed their apogee. And as we move through the 21st century, we're suddenly facing all of these challenges for which we have no technological solutions. We see the end of antibiotics, something we could have never imagined, where we're now vulnerable to even the simplest of diseases. As Dan talked about earlier, we only have about 24 vaccines. And as we saw with Ebola and MERS and SARS and H1N1 and even seasonal flu, we can't move rapidly enough to create an effective vaccine. We don't have protection against many of the infectious diseases that are occurring and likely to increasingly occur as we become more globalized. In the realm of material science, where I come from, we haven't seen a materials revolution since the 1950s that truly changed our world. And even as we see natural disasters or man-made disasters, we have no technology that can handle the complexity and the scale of the problems to actually fully recover. We need a new technology vector. Biology is technology. This is why DARPA formed the Biological Technologies Office. It offers us a chance to combine all of the advances that we've seen over the past 50 years in electronics, in physics, in computer science, in data analytics, and combine it with the last 2 decades of advances in genomics, in biology, and neuroscience, and come up with a technological capability that far surpasses anything that we have today. It would be truly astonishing to have a technology that could leverage both of these aspects from the engineering world and from the biological world. It could offer us solutions and capabilities that we just don't have today. When I came to DARPA 4 years ago, I came because I was frustrated with the pace of materials innovation. I was working in nanotechnology. We were trying to assemble materials up from the nanoscale to get new types of properties, and we were failing. We didn't have the tools that actually enabled us to manipulate matter at that scale reliably and controllably and reproducibly. The materials that we have today pale in comparison to those that biology can produce. If you think about something as simple as the human skin, something that's with us from birth, that grows with us, that can sense the environment, that can sustain a microbial community, that protects us from insult, that can self-heal, we don't have anything like this. Now, we've been trying to solve this problem by creating increasingly complex machines, increasingly sterile environments. But biology offers us a much more sophisticated platform. It's programmable, it can scale, it can manipulate matter at the nanoscale. It's hierarchical, it can grow materials from the nanometer to the millimeter to the meter. This is the manufacturing platform that I wanted to use. And so I started the DARPA Living Foundries program 3 years ago with a very simple goal. Let's use biology not just as a technology, but as a manufacturing platform. And let's go beyond those very simple biochemicals and biofuels that are simply substitutes for petrochemicals that we have in our world today. And let's capture that full space of complexity that biology can offer us. Let's create new types of polymers and catalysts, and let's go to the extremes and create materials that are multicellular and multifunctional and dynamic and have inorganic and organic components. Why can't we make these things? But the challenge was that when I looked at how biology was done, it hadn't changed very much in the past 100 years. Many of the approaches were still ad hoc, experimental work done by hand by highly trained graduate students, low throughput processes, writing results down in lab notebooks. The problem with this is that when the pace of innovation is based on the pace of humans, when it's on human scale, your innovations don't come very often. They only come in generations. I wanted to change this. I wanted to apply an engineering approach to biology, to apply all those advances in miniaturization, in automation, in electronics, in data science, and create a design, build, test cycle for biology where I could take a design in my mind and implement that, construct it into a DNA program, upload that into a cell, and then execute and run that program to get a new function. Maybe even something that different from what biology does today. So I want to take you through a few of those investments that we've done over the past 2 to 3 years. The first one is what Jack mentioned. We're essentially still using punch cards for biology. DNA synthesis and assembly today is slow, it's expensive. I can't build very complex designs. It's no wonder we can't get very far. And so working with Twist Biosciences, we decided to completely change how we even do DNA synthesis and assembly, moving from the ubiquitous 96-well plate that we're all familiar with to leveraging silicon micromachining to enable us to increase the scale and throughput by over 2 orders of magnitude, to bring down the cost similarly, and to increase our control so that we can actually make designs that work. Because once we can do that, we start to open up the full realm that we can explore in biology. The second example is that despite the fact that we have over 30 million species on our world today, we essentially only use 2 for engineering biology today, E. coli and yeast. What I'd like to do is I'd like to take any microbe that I could find out in the environment with beneficial properties, let's say heat tolerance or acid tolerance, and I want to engineer that as my platform. To do that, I need to read its entire genome and I need to map it. But the problem is if you look at the Genome Browser software that we have today, it's like looking at a genome through a soda straw. I lay out all the DNA as long as I can, so I'm showing that in the overview section above. And then I zoom in to about 1 KB, which shows the details. And I look at this tiny little snippet. This is fine if you're an academic researcher and you want to find something esoteric to publish a paper on. But if I want to engineer an organism, I need to see the entire system. I need to understand what's familiar and mundane and what I understand so that I can actually engineer it. And so working with Amyris, we worked with their computer scientists and bioinformaticians to build essentially the Google Maps for genomes, where I can take raw genome data and then give myself a map of that organism. And not only that, but I can look at it from a systems point of view. So here I'm looking at all the meiosis data on that organism. And so now within a day, I can now make an organism engineerable. And I can open up the full space of organisms to engineering. The third problem is one that you may not even realize is a problem. We all hear about how much genomic data that we're collecting. We have over a terabase in our databases. But the challenge is that most of this is unannotated. So if I want to go through those databases and collect information and actually figure out what program I want to write, I cannot do it today. The only information that is annotated is usually only available in scientific publications. And no single human being can keep up with all the scientific publications and piece one publication with another result from another one and, let's say, build up a new enzymatic pathway to get to a material that I care about. So working with 2 scientists at Berkeley, who ended up starting a startup company, what we did is we developed software that enabled us to map all of this genome sequencing and all of the papers that had been written so that, for example, we could collectively figure out the entire space of chemicals that we could reach. And so, for example, in the upper left-hand corner here, I'm showing you the class of terpenoids. So now if I have a material, I can actually figure out how to get there, and I can figure out all the enzymatic routes to there. And I can start to do interesting things, like, for example, I can highlight all the chemicals that are in the WHO essential medicines list so that I can figure out which ones are expensive and might be cheaper to make through a biosynthetic process. Now, the final technology I want to talk to you about is one that I think will have some of the most far-reaching impact, not just for synthetic biology, but all of biology. And that's getting rid of magic hands, getting rid of those 96-well plates and the limited liquid handlers. And that's by leveraging not just microfluidics, but the multi-trillion-dollar investments that we've seen in the semiconductor industry and in the display industry, so that we can actually start to scale our experiments to millions, and that we can increase the pace of them to, let's say, 100 kilohertz. And now I can span such a huge array of the biological space. And not only can I span such a huge array, but I can share my experiments with you, and you can simply code them up on a programmable platform and replicate those experiments yourself. If successful, this would enable people for very low cost to have access to these sorts of tools and do these sorts of experiments. And I think, as all of us know, revolutions happen when you get lots of people working on your problem, thinking about your problem, and innovating on it. And to do that, we need new platforms. So what's the impact of all of this? Prior to Living Foundries, because we relied on these ad hoc processes, to develop a new bioproduct could take you tens to hundreds of millions of dollars in around a decade. There's no way we're going to get to a materials revolution on that kind of pace. But within 2 years, we were able to show an improvement of over an order of magnitude, where we went from years to months to create a new bioproduct, and we went from tens and hundreds of millions of dollars to hundreds of thousands and millions of dollars. That enables much more people to get into this space. But there's a lot more work to be done. Not only do we need to bring the cost and time down, but we also need to open up the incredible space of complexity that biology offers us. So we're not just making simple products, we're making those amazing complex products, those dynamic products. And hopefully the impact will be another materials revolution. The last time we saw a materials revolution is when we went from using raw and natural materials from the environment to the petrochemical revolution in the 1920s, from the very first time we could actually design materials according to our needs. But we lost that complexity that we had in biology, that dynamic function. With the ability to genetically encode materials, we can combine these two realms. We can have the functionality and complexity of biology combined with our synthetic methods to reach materials that we've never been able to before. And the impact of these tools are much broader than just a materials revolution. They can open up entirely new fields because the language of biology is general. All organisms read the same code, and all of these tools leverage the same platforms. As Dan told you earlier, we can apply these tools so that we can come up with new ways to outpace infectious disease. We can think about new ways to control the spread of vectored diseases. We can think about alleviating resource constraints, such as water scarcity, the need for food and energy, so that we can maintain global stability throughout the world. We can transform environments after natural disasters and man-made disasters. And ultimately, we can transform hostile environments, not just here on Earth, but even beyond. We could actually start to think about not just going into space to visit, but to stay. That's a revolution. We're here today because we want to work with you, and we're looking for partners to begin this immense journey with. We're looking for researchers who have great ideas and who want to build tools and technologies to attack these problems. We're looking for potential program managers who have a vision that's so big, it surpasses any one individual organization. And we're looking for collaborators, people who are willing to bring those resources to bear to make sure that the technologies that we build in this office actually spur new industries. We want to work with you, and we're 100% dedicated to solving problems that matter. Thank you.